Okay, hello, good morning, everyone. And today we have lecture number 12 on the topic of today we will have lecture number 12 on the topic of active learning for material screening and optimization. Active learning is a relatively quite new approach of material optimization and screening. So basically, if we look at active learning itself, is about a query. So we try to actively query on the properties of the material in this case. And we try to optimize or try to select the materials accordingly. So what we need from the material properties. So that is roughly the idea of active learning for material screening and optimization. So we will look into this topic of active learning in details, and as well as we will look into a few examples of active learning for materials and MEMS application. So what is it all about? Active learning for material screening and optimization is an iterative, data-driven approach that uses machine learning to guide the search for novel material with desired properties. It is particularly valuable in material science because developing new materials through traditional trial and error experiment is a time-consuming and expensive process. So iterative meaning here, we can always go back to the data to look into what is the actual needs for that particular materials for the properties that we want. So that is the meaning of iterative here. And basically, it's a subset. Active learning is a subset of machine learning. So we know that in machine learning, basically, we have to have a lot of data in order to make it work. But somehow in active learning, we might not need that as much as data like the normal machine learning process. Somehow it's a part of a subset of machine learning. So we know that if we want to develop a materials or try to find a material, suitable materials, new materials, we do simulation. Nowadays you have a lot of software for material simulation, molecular dynamic simulation to predict the properties of a material. So in active learning, we try to do the same to get, when we try to design something and we try to derive material properties. For example, you have solder alloy. Then with a solder alloy, you know that you need certain temperature or melting point. Then you will need certain extent of Young modulus and tensile strength. So that is where you try to look into the existing data from experimental data. Then from that data, you try to predict or to get the properties right. So here, if you look at this and label, so this is schematic of simplified active learning model or process. So where you have your unlabeled samples. Unlabeled meaning you do not know exactly what is the data for, or that particular materials have what kind of property, or that particular materials what is good for. Then with that sample, we need a human, or we call it in this case oracle. So this oracle, we try to assist in labeling the materials or labeling the properties of the material. So with this labeling, then you have a training set. So unlabeled samples then go to the label sample. Then later on, you go to a machine learning model, which is a kind of simplified machine learning model with a certain properties. It might not be one property, but a couple of properties that required for certain application or purposes. Then this will kind of put a prediction to the performance of the materials. So this can be a loop of iterative process to have materials from unlabeled. You increase the number of labeled materials, you get the sample from experimental or existing data so that it can be looped. Then after some time, you will get the closest properties of the materials. So that is roughly what happened in the active learning process. The thing is better than the trial and error, because in the case of trial and error, we might do a lot of experiment in order for us to obtain certain properties of the material. We have our own hypothesis. For example, the hypothesis might be, if you, let's say I give another example of solder alloy, for example, materials. So in the case of solder alloy, you might want to have certain temperature, and the temperature, the melting point, the melting point might be around 220 for SAC solder alloy. Then with that, you try to predict the melting point if you add another materials to it, and in terms of your application, and you want to know the tensile strength and the modulus of the materials, the Young modulus, etc. So the existing data label, if you want to do with a traditional trial and error, it might be taking a lot of time. If you include another element into the materials, so hypothetically, you might need to do experiment, to conduct a few experiments in order for you to obtain the right properties that as intended. So this will consume a lot of time, a lot of resources, and it not necessarily will get to the endpoint that you required. So here is a time-consuming and expensive process for trial and error. So how this process, let's say, if we look at a normal process of materials development or materials for certain application that we try to do with a certain process. Let's say here you have scandium aluminum nitride piezoelectric materials. So traditionally, it will take about, if it's through traditional development, it might take 2 to 3 years. With active learning, so with existing data, for example, we can have maybe lesser time, 3 to 6 months, for example, which is 6 times faster than the process of traditional development, like try and error, where you try to include certain new element to the materials, or you try to iterate the process of producing the materials, for example. And it goes the same with high K dielectrics, for example. You will need 1 to 2 years with the traditional development. And with active learning, it can be shortened to 2 to 4 months, for example. And it's here, if you look at this timeline, you can see that it's 5 times faster in comparison with a traditional development process. And if we go look into a low stress silicon, for example, it might take you 6 months for the development, and for the active learning process, 4 to 6 weeks. It's 4 times faster. And for thermal interface is a material that you use to connect chips or electronic device, which you try to remove the heat. Like heat sink, then you have a thermal interface connected between your chip and the heat sink, so or heat remover devices. So thermal interface also might need 1 year for the development, and with active learning, 2 to 3 months might be possible. So it's 5 times faster. So the difference is in traditional screening, grid search or intuition based. Grid search meaning we have a lot of data prior to this, then we try to include certain new knowledge that can be obtained from some other sources, published article, for example. Then with that, we try to have our hypothesis. And also sometimes based on intuition. So intuition meaning those who are very familiar with certain materials development or certain field of research or expertise, then one might have a certain level of intuition to work with something. And 100 to 1,000 experiment, typically this is might be maybe a little bit exaggerated, but if it's the scope is big, let's say you want to have multiple properties to be optimized or to be selected for a material, so you might somehow need this kind of experiment, and the cost of development might become 100,000 dollar to $1 million, for example, and high risk of missing the optimal. So, meaning to say, still we are doing it kind of trial and error for at certain extent. Then we, for example, we want to optimize certain properties in the solder alloy. We might, referring to literature, we might go into certain materials to be included, certain element to be included into the alloy. And firstly, you might go with the different weight percentage. So the weight percentage might be optimized accordingly because it's just, some interval in terms of the addition of the materials to the new element to the alloy. So that might have some risk that you don't get the optimal value of the properties that you are intended for. But instead of that, for the active learning, it's more intelligent and adaptive sampling, meaning to say you have your materials and the properties that have been reported, then you label it according to the property, which is the kind of exact accurate property. Then with that, you are doing iterative and to look for the property of the material. And it is 10 to 50 experiment might be sufficient, and 10 to 100K development cost, which is very much reduced in comparison with a traditional screening, and it's a systematic global exploration kind of process. So, however, in the MEMS material challenge, the traditional approach of materials development or MEMS device development is might be much more bigger. So it's a vast search space where it's about million and a billion of possible composition, basically, expensive experiment, as we know, and the time intensive, weeks per iteration that you need to do, and it's very time consuming, because in order for you to prepare certain materials, it might take some time, and do the characterization also might take a lot of time as well. So that the whole process will be a lot of time consuming process. And limited exploration, less than 1% of the space typically sampled. So basically, we are limited with our sample and with our time, and also with the possibility of to do things. So we try to narrow in terms of the development from the beginning, then this will happen. Human bias, focus on non-material classes. So this is always the thing we try to refer to the properties of the material from the literature, for example, from what being reported. Then with that, we have certain bias towards certain property of the material or the non-materials. And for MEMS specific requirement, for example, in a material for application in MEMS, we know that we are looking into material for mechanical properties, for electrical properties, and for thermal properties. This kind of property might be a more complex system, a complex property of the material that you need to look at certain extent at one time when we try to develop the material. And of course, if you have active learning, this might be more simple in comparison with a trial and error development. And size constraint, thin film and small features. So in this manner, it might have a different property in comparison with the bulk material. And the small features also I mean, as we learned before, it will have a certain property that might be different according to the scaling laws. And process integration, CMOS compatibility, for example. So it's not just about the MEMS device has to perform with mechanical properties or electrical properties or thermal properties as intended, but it has to be compatible with the process of some other devices, for example, the CMOS. And it has to be reliable, 10 to the power of 9 cycle extremely in extreme environment, for example, and cost sensitivity consumer application. So if it's about things with a consumer application, we have to know that there have to be some limit of things that will be acceptable to the market. If it's too expensive, then people might not be able to afford. So the opportunity here, active learning can intelligently navigate this vast space of exploration of the material properties and possibilities, focusing experiment on the most promising region only. So meaning to say, if you have data, existing data, and you can label it accordingly, so some focus region might be possible. So the difference between active learning and passive learning. And passive learning is a random, fixed data set and needs large of data set and slow discovery. So as I mentioned before, so you might have a limited data set and you have to explore the data set, and it's fit within your knowledge of the data or component of the things. And the thing is, you might need a lot of data set in order for you to be convinced and to be able to know that the certain properties is kind of acceptable. And of course, as I mentioned before, it's a slow discovery in order for you to get the information. And but for the active learning, it's a model-driven selection, and it's learned from fewer data. Firstly, it's not, you don't need a large of data set, but it's a kind of accelerated discovery. So in machine learning, normally you need a lot of data, but in this case, if it's active learning, even though it's a machine learning process, but to a certain extent, it's a query, it's an active learning where you have a different algorithm for you to look into approach in order for you to have a different data set. So the features of active learning. So basically, query strategies select label for training the data. And for the passive learning, more adaptable for dynamic data set. And for data selection, so as I mentioned, query strategy, select data for training. So firstly, you have your data to be labeled. Then you have the query happen when you already get the data for the processing or try to identify the properties. And for the passive learning, data selection, the entire label data set is used for training instead of here. If you look at the active learning, is the select data for a training strategy. So meaning to say, it will select certain data and query on the properties, for example, in order to get the information accurately. But here, the entire data set will be used for training for the passive learning. So cost uses human annotator. So human need to label the data. So expertise can be expensive. So this is kind of the drawback in terms of active learning. So you need to have a kind of expert. And for passive learning, no expert needed, use entire label data set. And in terms of performance, improve performance with fewer labels by selecting informative samples. So the package of the samples or information required for certain properties might be different. So with that, you limit your sample, and you can select a sample which is favorable or sample with sufficient information for the process. And longer training and more data needed for similar performance, and adaptability, more adaptable for a dynamic data set, and passive learning adaptability is limited by the availability of data. So that is the difference between these two. So the fundamental of active learning. Basically, the core philosophy of active learning, instead of randomly sampling the material space, we use machine learning to intelligently choose which experiment will be most informative for building accurate predictive model. So meaning to say, we don't go for everything, but we selectively look into materials or process or experiment might provide you sufficient information for you to do the prediction of the property. So the process begins with a small label data set. This is the initial process. So this data set then trained a surrogate model. For example, surrogate model is a very simple model in comparison with a normal model of machine learning. Then a query, and select most informative point. So within the information required for the materials, we might go into a more informative point or specific scope of information that actually will be benefit for the prediction. And experiment, synthesize and characterize of the materials, then update add result to a data set, then repeat until a convergent, until we get the property as intended or what we want. So the model's uncertainty guides where the experiment next, ensuring each new data point maximally improve our understanding of certain properties or certain materials as we want. For example, here for active learning for material screening, an active learning process for material screening is an iterative closed loop and closed loop methodology that combines machine learning with experimental or computational calculation to efficiently discover materials with target properties. So the process intelligently select the most informative new material candidates from a vast pool, reducing the number of expensive time-consuming material experiment or simulation required. Meaning to say, with a certain data set, the focus property of the material will be selected from the beginning in order to look for the possibility of iterative or data set to be labeled. Then it's closed loop methodology where you, from the labeled data set, then you repeat the same thing with some other unlabeled material to be labeled. Then the process happens again and again until it's converged. So, and it can be the mix of machine learning with experimental data set. So from the data that obtained from experiment, or computational calculation. So computational calculation might be data that established with the simulation result obtained from somewhere, or you can also do by yourself for the computational properties of the material. Then with that also it can be used in this active learning. So the process intelligently select the most informative new materials candidate. So the most informative meaning the data set that say you want to have a few properties for your material. So is it all the data set for the properties is available within the material that you have selected, or the unlabeled material that you're going to label to have the properties as intended. It's not that one by one that you have to combine. And if you see here, and for example, with a composition of certain materials alloy, you have certain features. With this alloy, for example, you have titanium, nickel, copper, iron, PD 22 initial alloy, and delta T were measured. So the valence electron number information might be available, and electronegativity might be available here. Then you have the metallic radius information, you have atomic radius information, then you have a petit four chemical scale. Then in these features of what you want from this alloy, you have your interface, for example. Then you train the model for the predicting of delta T from features with associated with uncertainties. So then you go to the unexplored alloy. So unexplored alloy meaning, let's say you have other than what you have understand here. So try to look into that certain alloy if it can match or the information given by this unexplored alloy can be used. I mean, can be something useful to get the alloy new composition for the alloy you're going to develop. So the delta T predicted from model with uncertainties. For example, so you have your XYZ properties here, XYZ, maybe the weight percent of the material can be decided using active learning. So then you can design the materials accordingly. Then, of course, this need to be experimental in order to confirm what being predicted by active learning here is as intended for the properties of the material. So this will save a lot of time in comparison if you want to do the process with properties of the material. Let's say we find the property of the material from journal, from a reported article, then we try to mix the material with certain element. Then with that element, we might have the bias of certain percentage as reported. Then, as I mentioned before, it might not be optimized because we have the certain value which is available, then we try based on that value. So that might be the missing point if we use a conventional process of materials development. So active learning for material scanning, basically, number one, you label data. The label data is a small data set with a non-output used to train an initial model. So you does not require a lot of data set. So with a limited data set, but somehow with information, comprehensive information as required by the intended property. So it does not have to be so comprehensive outside of the property that you want. So it can be the property within the material that you try to develop. Number two, unlabeled data is a large pool of raw data from which the algorithm strategically select the most informative example to be manually labeled. So here we see that it has to be human to be to label all the material or information as the material provided. So this will be someone who have to have expertise in a certain area. So the label data here, label data has been manually annotated with a meaningful text or classification by a human expert. In active learning, this data set serves two key purposes. Number one, initial training. The process begins by training a preliminary model on a small, high-quality set of label data. So high quality meaning the data is accurate and within the scope of information required. So this is for initial training. So, secondly is evaluation. So once the initial model is trained, the label data is used to evaluate its performance and inform the active learning process. So this is evaluation and query. So where it will evaluate the performance according to the information that obtained from the label data. So for example, For an image classification task, a label dataset might consist of 100 images of cats and dogs, with each image explicitly tagged as a cat and dog. So that is label. So you have let's say 100, I mean, as mentioned here. So you do not know whether the image is a cat or dog. So this is where the human expertise will be required to identify cat and dogs from the beginning to label it. So this is a quite simplified uh, 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 process, but somehow if you look at the material properties, it might go beyond that, meaning to say the property might be not just two property, but a few properties that required by the data or the materials development. So for unlabeled data is raw, untagged information that is abundant and inexpensive to collect but lacks classification. Active learning harnesses this data in the following ways. So the data is a vast data. So before we label it, so active learning needs this data to be labeled before it can be processed by active query in the machine learning. So this vast data is where it might be difficult, even though it's inexpensive data, but to have someone to label might have some expertise required. So large pool, the vast majority of the data is in an active learning scenario exists in an unlabeled pool. So unlabeled meaning you do not know whether it's a cat or a dog from the beginning, then you need to label it in order for the machine to understand. And source of queries, the trained model use a query strategy to identify the most valuable examples from this pool. And the most informative example are those that the model is most uncertain about, meaning they are likely to improve the model's accuracy the most if they are labeled correctly. So the correct label is very important in order to predict the right property of the material that you're going to develop. So example, for the same image classification task, the unlabeled data would be thousands of additional raw images of cat and dogs without any text as whether it's cat or dog. And the active learning model would identify a specific ambiguous image. And for example, a cat image that looked somewhat like a dog. So as particularly informative and request a label for it. So if it's ambiguous, the active learning, the query process is to confirm, to identify whether it's a cat or a dog to be a label. So the typical active learning workflow for material screening is a cycle of 4 key steps, basically. And start with an initial data set. This, as mentioned before, the process begins with a small curated data set of materials, their properties and structural or compositional features. So it depends on the data set or the development that we required. So we look into the properties as what as intended or what is required. This initial data can come from existing material database, a prior experiment, or a small number of randomly selected and labeled samples. So as I mentioned before, we get the data set to be labeled from experimental report, or from experiment that we do, or the available data anywhere that provide the information that we require. And number 2, train a surrogate machine learning model. A machine learning model often Gaussian process regression or ensemble of models is trained on the current label data. So the training need to be done for the data set in order to understand or to identify correctly what will be needed for the development. This model, also known as a surrogate model, learns the complex relationship between the materials features and their target properties. So basically, the model might be able, if you have the properties of the material with the material information, then how it can be relate to the intended properties of the material. So identify the next best candidate. The trained model is used to predict the properties of a large pool of unlabeled potential materials. The core of active learning is the query strategy, which uses the model prediction to select the most informative candidate for the next round. So it's a few rounds of process where you need the information to be maybe from step to step of a dog, how it look like, then you identify the next information, then with that more informative features of the material, you can be more confirmed of this is the material that have been the same thing within the same group, for example. So that will is the machine learning to proceed for the prediction of the material properties, meaning to say the information is very well informative. And number 4, perform experiment or calculation. The materials candidates selected by the query strategy are then evaluated through physical experiment or high fidelity computation, like DFT, density function theory, or molecular dynamic simulation. So as I mentioned before, this experiment provide the labels, the true measures of properties for the selected candidate. So maybe nowadays we do the simulation based on our intuition to have a certain materials or element, then we do simulation. So the element added to the material might be due to the properties that we obtain from some literature. But of course, if we can do the active learning before we do simulation or experiment, it might be more favorable in terms of getting the result correct, because at certain extent we have understand the property of the material accordingly due to machine learning approach. So here the experiment, or you can start with a DFT or molecular dynamic simulation to look into the property. Then after that, you can proceed with the experiment. So this experiment provide the labels, the true measure properties for the selected candidate. So this is to confirm what has been predicted by the active learning process or the machine learning for the property of the material. Update the dataset and repeat. The new data from the experiment are added to the initial dataset, which is then used to retrain the surrogate model. This close the loop, allowing the process to iteratively refine the model predictive power and converge on the optimal material with far fewer resources. So whatever has been predicted before can be fit in again with the simulation result and also experimental result in order to get the model to be more accurate. So the model here will be able to have more information or correct information, true information, which is will be very beneficial for the next prediction or to get the optimal value of the property of the material. So this is a active learning loop. So you have a input data set for the material. So let's say material features X, for example, with the property of electronegativity, ionic radius, volume, ionic displacement, polarization, and dopant effect and on transition available. So then you have your target property of Y. So with this, with statistical inference and machine learning, so you have Y equal Fx plus uncertainties, for example. then you have a possible compound of 60,000, 605,000. Okay, then that is the possible compound. Then next, design and optimization, choice of candidate for the next experiment. So is within the whether you do exploitation or exploration. So this will require a lot of information as well, and trade-off between exploitation and exploration. This is what good about active learning, because you can see the trade-off between the exploitation and exploration. So then also a random selection. So then the 4 recommended samples for synthesis and characterization can be done. Then next is the synthesis and characterization. As mentioned before, at this stage, the material properties will be kind of revealed. You can obtain the materials through properties through experiment or through simulation. Then you feed back to the data set to label it to the data set that this is the new material or new compound that have a certain property as what being learned from here. Then it will fit and try to make the input data set, then go through the statistical inference or machine learning again in order to improve the accuracy of the model. So as a framework of this machine learning process, so the mathematical framework, the acquisition function in the mathematical brain of active learning. So the expected improvement, for example here, EIX equal sigma x, then Z equal micro x, F, and divide by sigma x, where you see that micro x is the model predictive value, and sigma x is the uncertainty, and F is the current best result. This function balance the exploitation areas of where they predict high performance with exploration areas where everything is uncertain. Then for the upper confidence bounds, or UCB, this is a simpler but very effective, basically. And the parameter kappa control the exploitation trade-off. So this kappa basically control the exploitation and exploration trade-off. And higher kappa means more exploration, and lower kappa means more exploitation of non-good region. Region here meaning the scope of the property of the material. And the probability of improvement, PI, this calculate the probability of beating the current best by a margin of xi. So that is the mathematical framework of this acquisition function. And next is in the real material application, we rarely optimize just one property, and we want high dielectric constant and low leakage and thermal stability. So if this is in the case of semiconductor materials, so that is where we need to have multiple properties. It's not just one property, but it become more complex. So that's why multi-objective expected hypervolume will be used. So this optimize multiple properties simultaneously by considering the hypervolume dominated by Pareto frontier. So here it will be the expected hypervolume where you can optimize a few properties at one process. So here the mathematical beauty of this function is how they balance two competing needs. Exploitation focus on region where we expect high performance, And then we have exploration, where we investigate uncertain regions where we might learn something surprising. So traditional approach tend to be either purely exploitative, and meaning to say is with a lot of data and difficult, or purely exploratory with a random research. So whether it's random or exploitation, so that might be the difficulty. But active learning optimally balance both exploitation and also exploration. So material specific consideration, material science present a unique challenge in here. So that distinguish it from other machine learning application. So unlike image recognition or natural language processing, materials don't come with obvious features. So we need to engineer meaningful descriptors that capture the physics and chemistry when we label the materials, so that the machine learning will learn accordingly. So this is a kind of the basic properties of material that normally we fit into the system or try to label in the machine learning. For example, the basic properties of atomic number, mass, and radius. Then electronegativity, ionization energy. So this will be kind of the base of the material that will shape the property of the next that we intend to have. So the electron configuration, melting or boiling points of the material. So with this is the basic property of elemental features. So statistic descriptor, we have a weighted mean, then we have variance, skewness, and a mean max range in terms of the statistical descriptors. Then we have a structural features and a crystal structure, for example, space group symmetry, coordination numbers, bond length, angles, and packing efficiency. Then we have another features, which is the processing features, deposition temperature, pressure, atmosphere, annealing condition, and film thickness. These are all the material features in engineering. When we try to use in certain application, we need to consider, because it's just not about the performance of the material as intended. For example, in MEMS, we are not just looking into the mechanical properties, electrical properties, and thermal properties. For example, we need to look into the electronegativity, depend on the application again. Then on top of that, how it can be compatible, how it can be processed, compatibility with some other process. So that is where things get more complex and complicated. For example here, features type, elemental mean, example, mean atomic radius. Then for MEMS relevance, you have to look into the lattice parameter. So this can be calculated by this. Then another thing is for example here, size mismatch. So example is delta parameters. Then you have a solid solution stability. Then you can calculate by this equation. So another thing, for example, the bonding characteristic of MEMS. Then you need the features of electronegativity of the material. Then, for example, you have delta E and the variance. So these are features, example, and the relevant into the in terms of MEMS material. And the query strategies for active learning. So uncertainty based, when to use it. For example, when to use with a single objective optimization, will define a target property and want to refine the current best. Meaning to say, we are uncertain of certain properties, then we need to refine it with if it's a single optimization, meaning the single properties of the material need to be refined or optimized. So that is where we look into a specific target of the property. So the diversity base when to use in the early exploration phase, an unknown search landscape, and want broad coverage. So meaning to say, from the beginning, we are covering a broader scope of the property, then we can have a property of try to explore or try to improve might be a more bigger in terms of number. But in MEMS, the hybrid strategies for MEMS, exploration phase might be first 20 to 30% focus on diversity sampling materials and cover different composition region. So composition region might be referred to the required property of the material according to the need later on, and include processing parameter space and build initial model understanding. So to include processing parameter space is to know that whether you can process with certain, let's say, MEMS for using etching, or you have a CVD or addition with the materials, etc. This is exploration. So at the first stage, then exploitation phase, finally a final with a 70 to 80%, and switch to expected improvement. So from this, you try to improve further and refine promising region. Region meaning the number of properties that might be required for the material. Then multi-objective optimization with maybe conflicting or different properties of the material. Then you validate the final candidates of the property. So common MEMS trade-off. This is another example. For example, piezoelectric material. If you want to screen and optimize piezoelectric material, you have to look into the trade-off, the response and stability. So response meaning the material that have a property of piezoelectric coefficient. How let's say here in the case of D33, is it high versus the temperature coefficient? Temperature coefficient is whether it will have expansion with the change of material, or it degrade with a change of the temperature. And coupling versus loss, and voltage versus power, coercive field and remnant polarization of the material. This is in case of a piezoelectric material. And in case of mechanical resonator, for example, you have Q quality factor versus a frequency, the damping and the stiffness of the material. So you know that stiffer material will have a high frequency. Okay, stability versus sensitivity, then size versus performance, which is we look into the miniaturization limit. So how small it can go. So in the multi-objective approach, we try to look into Pareto frontier, where find non-dominated solution. Then you weighted the sum where you scalarize the objective in this case. So that is the process. Then we refer to the previous multi-objective equation. Then you can get the multi properties that required or intended. So surrogate model for materials. Surrogate model is a simpler data-driven mathematical approximation that replaces a complex, computationally expensive original model, such as finite element analysis, a physical experiment. By training on a limited set of simulation or experimental data, the surrogate model can quickly provide accurate prediction, estimate uncertainty, and facilitate tasks like design optimization, sensitivity analysis, and exploring design space, which will be impractical with the original model. So the Gaussian model is one of it. You have a few advantages of Gaussian process model. The advantage is uncertainty quantification and you have a small data performance, and physics informed kernels, and hyperparameter learning. So this is the advantage of Gaussian process, and the random forest also have a few advantages, and the neural network also have a few advantages. But of course, you can choose whichever is more convenient and more practical to be used. So we look into the case study. Case study number 1, scandium aluminum nitride piezoelectric optimization in terms of the property itself. For example, the problem set up here, the goal is to maximize D33 piezoelectric coefficient in this material, SCAIN, and the search space is scandium fraction of 0.1 to 0.5, and the processing temperature is about 200 to 600 degrees Celsius. And the constraint here, crystalline quality, stress less than 500 megapascal. So budget 50 experiment over 3 months. So this is the kind of problem statement from the beginning. So the experimental details, for example, you need to do co-sputtering with a gradient, meaning to say because this is alloy with scandium, aluminum, and nitride, so you need to co-sputtering the material. So that is the process constraint of this material. And characterization that will be used, XRD, to identify the elemental analysis, stress, and D33 measurement, the piezoelectric D33 coefficient. And the features is composition, temperature, and film thickness. So the result here, for example, number of experiment, in the traditional way, it might be more than 200, but in active learning, 47 experiment might be sufficient. And for time, the traditional way of doing this might be 18 months, but here as the experiment might be less, than it will take about 3 months in terms of the development. So here might not be the optimized best D33 coefficient. So with the traditional way, with the composition done, might be 18.2. But here, because the active learning, the composition is optimized, then you can get the best, much better than what can be obtained from the traditional process. Then the optimal percentage of scandium, this is weight percent, 35%, then this is 42%. So active learning discovered that optimal composition was near phase boundary with narrow processing window, something missed in the traditional screening. The traditional screening might not be able to optimize accordingly. So, and second case study for high K dielectric screening. So try to optimize this material, hafnium, zirconium, titanium oxide, composite for MEMS capacitor, balancing dielectric constant and leakage current and thermal stability. So normally dielectric, you look into dielectric constant, leakage current and thermal stability. So that is the required property of this material. So the experimental design here with a 3D composition triangle and processing ALD temperature of 200 to 400 degrees Celsius, and the target kappa more than 30, etc., and budget sample 75. And active learning is multi-objective expected improvement because you want to optimize a few property here. So, and the Pareto frontier optimization will be used, for example. Then here, the discovery is the composition of different HF, ZR, and TiO3. Here, 0.4, 0.3, and 0.3, and 2, for example, you get the K47, and you get the J 2 times 10 to the minus 7, for example. And another composition of hafnium, you get K at 52, and another composition K at 41. So this multi-objective optimization revealed fundamental trade-off. Highest kappa material were thermally unstable, and Pareto frontier provided designer with choices based on application requirement. So you can tailor accordingly due to what it will be used for. So another case study is a piezoelectric microstage. I think since the time is I skip this case study. So we go to the uh, conclusion of this. Basically, we want to, at a certain extent, it's not just about doing active learning to screen the material and optimize the properties, but at a certain extent, it's about getting the ROI, return of investment, and whether we can reduce the cost or we can reduce the uh, materials price, etc. So that is also part of the objective when we do to obtain the material properties using active learning. So with that, I thank you for your kind attention. Any question? No question. Thank you very much. Then in 2 minutes, we will continue to the next lecture. Thank you.